Hi everyone, my name is Fraser Cain. I am the publisher of Universe Today, and this is your weekly space hangout for October 4th, 2012. Now, if you're listening to this in the Astronomy Cast podcast feed, I want to remind you that we record the weekly space hangout live once a week, every Thursday at 10 a.m. Pacific, 1 Eastern, and math 6 Greenwich Mean Time. So if you want to watch us record live, you can always join us right on Google Plus. So joining me this week, we've got let's see who have we got. We got Amy Shira Teitel from Vintage Space. We've got Nancy Atkinson, my co-conspirator at Universe Today, and we've got Nicole Gugliucci from CosmoQuest, aka the Noisy Astronomer. And we've got a few topics for you guys this week. It's a very strange week. It feels like a bit of a calm before the storm. Last week was an absolute zoo of space news, and we were all sort of having to get ready for a great big press conference from NASA. And so there's one great big story that was released, and there hasn't been a lot of other big news this week. So we've got a few interesting stories, but not the big news. So we're going to talk about the ancient stream bed that was discovered on Mars by Curiosity. We're going to talk about the Square Kilometer Array in Australia is moving forward. We've got a strange cold layer on Venus, the most precise measurement of the universe's expansion, and happy launch birthday Sputnik 55th. So let's get rolling. So first we got to talk about the big space news, which was this ancient stream bed on Mars. And so last week when we did the weekly space hangout, we didn't know that what NASA was going to be announcing. We knew they were going to be analyzing Jake the rock, and so we thought that there was going to be some results from that. But in fact, there was actually some really big news announced. So Nancy, you covered this a bit. So what was the announcement?
Well, yeah, we when we had to dash off last Thursday, I kind of figured it might be some big news because they did televise it on NASA TV, but I was really surprised at this. So the Curiosity rover team said that the rover had come across a place in Gale Crater where they said years ago, millions of years ago, ankle to hip deep water once vigorously flowed. So what they found was an ancient stream bed, and the gravel that was there that they found showed indications that it had been worn by water. And all indications were that the water flowed for a long time, as opposed to kind of the flash water events that people have proposed in the past, which would have created the now dry waterways and gullies and other features that we see on Mars today. What they saw was what they called water-transported gravel, gravel that has been worn down into small pieces by water, and that the gravel is now embedded in or kind of cemented in rock, which they called a conglomerate. And from the size of the gravel found by the rover, the science team was able to say that they thought the water was moving about a meter per second, and that the water was somewhere between ankle and hip deep. Now, this coming from the team really amazingly early into the mission was really surprising, and I, for one, was surprised at how soon they could make this determination, especially since the rover hasn't been there all that long. And but what they said is that they've really, from the orbital images from HiRISE, from the Mars Reconnaissance Orbiter, they've been able to see indications of, alluvial fans and flows coming into that crater, into Gale Crater, and so it really didn't take them long to come to consensus that this, when they saw this gravelly, water-worn rock, they were, very quickly able to come to a scientific consensus that that's what they were seeing, water-worn rock. So the area that this is, it lies to the north rim of Gale Crater, and it goes to the base of Aeolus Mons, or Mount Sharp. And again, the abundance of channels and the gravel that they're seeing suggests that the flows continued or repeated for a long time, and not just for a few years.
Yeah, I mean, I think the way that the folks at NASA described this, this is almost like if Curiosity went to Mars and discovered this ancient stream bed, it would be mission accomplished, right? And they're already, this is just the first couple of months of it crawling around the surface of the planet. So, to come across, because I mean, we've mentioned this in the past, right? That the goal here with Curiosity is that they're not looking for life yet, because apparently that's forbidden. But they're looking for evidence that there were conditions on Mars in ancient times that life could have existed. So you want water to have liquid water to have been on the surface for a long time. You want the kinds of chemicals that would have been present with life there, an energy source, something like that, all at the same time. And so to find this ancient river, I mean, I've got a river like that near my house. You can go down and you can find these smooth rocks that have been jumbled around like in a great big rock tumbler for 1 million years, and that's what you see. You look at that picture, the pictures of Mars. I don't know if someone has one of those pictures. We can maybe put that up in a second. But you look at those pictures and you can see these, round rocks all collected together. It's just a stunning finding. It was not at all. I was completely surprised when they actually announced it in the press conference.
Yeah, and they basically said, though, I mean, they've already moved on from this spot. It's like, okay, found that, we're moving on now, because they said that this actually was not a place to really find organics. Where they really want to go is the base of Aeolus Mons, where they've seen from orbit that there are clays, layers of clays, and clays are a very good preserver of carbon-based organic chemicals that are potential ingredients for life. So basically they found the water evidence and said, okay, found that, check that off our list, and now we're going to go find organics. Yeah,
it'd be like going on your way to turning your lottery ticket for $1 million. You bought another lottery ticket, and that also won $1 million.
Yeah.
I love it.
Pretty amazing.
So what's going to be happening next? I know there's another press conference today. So what are the plans?
Well, they're on their way to the Glen Elg region, which is another interesting region that they saw from orbit. That's kind of a conjunction of light and dark materials, and I think there's possibly some clays there. I know this week that they were testing out the scoop and the ovens that they're going to put the soil samples in and test that out. I don't know if they've done that yet, and maybe we'll find that out today.
Oh, it's going to be fantastic. Maybe they found life, but I don't think so.
This one's not televised, so I'm thinking it's just a basic update.
So someone is asking, how does the Curiosity team know it's actually liquid water as opposed to some other liquid on the surface?
How do they know? Oh, like how do they know it's like not liquid? Well, I mean, there are no other. I mean, when you look at the rocks, you see that there are these round, as I said, rock tumbler rocks, and so you would need some kind of situation. Now, I'm not a geologist. Emily was busy, I think, working on another.
Yet another amazing story.
Yeah. But usually Emily Lochtewal is the person who comes with the rock science. But you need to get the kinds of shapes. You need liquid to be operating on these rocks for a long period of time to get these round, smooth rocks, as opposed to jaggedy volcanic rocks that you would see. And so what kind of liquid can operate on the surface of Mars? It can't be liquid carbon dioxide, because it wouldn't exist, it would just sublimate in the atmosphere. Right. So it needs to be, I think, what other liquids are there? So I think that's the...
Yeah, I think it's the most likely, and it lines up with all the other evidence that we've seen.
Yeah.
Yeah, and Emily does have an extended interview on the Planetary Radio this week with Matt Kaplan talking about this. So she might. I haven't listened to it yet, but I'm sure she's got some more details about it.
I highly recommend always listening to what Emily has to say. She is a human geologist computer. She's quite definitely has her information. So that would be a great interview. I haven't listened to it actually. I should. Okay, great. Well, let's move on. So there you go. Huge news. Everything else is going to pale in significance. So I apologize in advance. So, all right. Well, then, Nicole, let's talk about the Square Kilometer Array.
How can the Square Kilometer Array pale in significance to anything.
Well, you're a radio astronomer.
You're a little biased.
You're a little biased.
Okay, so there is some news coming out of the Square Kilometer Array, specifically the Australian site. As you may remember, the consortium decided to split the telescope between two sites, surprising no one, between the South Africa and Australian sites. And the Australian Pathfinder project known as ASCAP, which is the Australian Square Kilometer Array. Pathfinder, I love those acronyms within acronyms. They make me so happy. That is opening nested acronyms. I could give you a list, but we'll another time. So they achieved something known as phase closure back in August, and so they're actually opening the telescope October 5th, which is tomorrow for those of us in the U.S., but it's actually today because we're talking about Australia, and they're doing a live webcast as well to dedicate the dishes at noon Perth time, which is 11 p.m. tonight Central Time. Good luck figuring that out from there. So I'll be tuning in for the webcast. The SKA is, of course, this huge, massive telescope that's being planned for the, I want to say, 2025 timeline. And the ASCAP is a Pathfinder. They're testing the technologies at the site where the telescope will be built. And so this Pathfinder itself is going to be doing some interesting science, looking at galaxy formation, gas evolution, and I love that because it is in Western Australia, some of the large surveys that they are planning to do are named things like emu and wallaby and dingo and possum. They've really run away with the animal names for the names of some of the large field of view, large bandwidth surveys that they're planning. Which is pretty fantastic. And also, there's a really cool time-lapse video. Oh, look at that! There's an image from a really cool time-lapse video that Phil Plait posted yesterday, I think, of the ASCAP telescopes, which you should check out because it's those really cool time-lapse videos. And if you've ever gotten a chance to see the Milky Way from the southern hemisphere, if you're one of those lucky enough to live there, or if you visited, it is really stunning because you can see the center of the Milky Way and you can see the Magellanic Clouds, and I think that video highlights all that. Even though in the radio you're seeing something completely different, but that's the same galaxy that we're looking at with radio telescopes.
Cool. I was trying to get that to pose. I can see it, and
you can see
if I was more prepared, I could probably post it. Yeah,
in the Google Plus thingamajigger.
And we have it on Universe today as well.
Yeah, I wish it was easier for us to push video into the Hangouts because that's one of the complicated things.
Yeah. So check it out, and I'm looking forward to the awesome science that's coming out of ASCAP, and its corollary in South Africa, the Karoo Array Telescope, Cat 7.
Cool. So what do you think will be one of the biggest scientific questions that the Square Kilometer Array is really designed to help answer?
One of the big questions is it's looking to map hydrogen back through pretty much all of cosmic time, right? So it's got this wide field of view, this wide bandwidth. So back to the epoch of reionization, which is what the low-frequency telescopes are aiming to do. Some of the Pathfinder telescopes, like the one I was involved in, paper, are looking to detect this hydrogen signal and give us our first glimpse of what the first galaxies were like. But something like the Square Kilometer Array is going to be our first step to actually imaging this hydrogen and imaging these bubbles of gas as they ionize, which is pretty spectacular.
Right, and so the epoch of ionization, this is this moment when the universe went from completely opaque to transparent. And after the Big Bang.
Well, not the same as the cosmic microwave background. That's when it went from opaque to transparent. Reionization is the hydrogen went from, so you could see through it, but it was emitting radio light, whereas now it's all ionized and it's not emitting that 21 centimeter line anymore. So if you had big 21 centimeter eyes, then it went from opaque to transparent.
Right.
Yeah.
But it's essentially, permeates. It's in all directions. It's one of the most distant things that we'll be able to see.
Mm-hmm. Yeah, it's about 500 million years after the Big Bang to 1 billion years after the Big Bang.
Very cool. Okay, so Amy, you talked about a strange cold layer discovered on Venus.
Yeah.
Venus, isn't that a hellish hellscape?
Yeah, it's like the Earth turned inside out. Yeah, the average surface temperature on Venus is about 890 degrees Fahrenheit, which I don't have the centigrade measurement in front of me right now. But it's hot, like really, really hot. And
It's about 380, I think.
Nice. I'm always impressed that people can do those conversions in their minds.
I didn't do that in my mind.
Oh.
He's Canadian! Don't they use that normally?
Yeah.
Yeah, so am I, but writing for Americans, you have to
Oh.
do everything Fahrenheit because nobody knows what you're talking about.
I'm sorry. I apologize.
But the European Space Agency has found that there's actually a layer in the atmosphere about 75 miles above the surface along the terminator that is minus 283 degrees Fahrenheit, which is, I think, about minus 170 or so Celsius. So that's really cold, and that's like a frighteningly large, difference from the 890 degree surface temperatures. So this is still pretty preliminary finding. They don't have a really good explanation as what's going on yet. But there's something about the way that the chemistry in the atmosphere is interacting with itself, because you've got the hot day side and then the night side coming together, and then you've got these weird levels of the atmosphere that apparently have different chemical compositions. And if I don't know, Nicole, that you're an astronomer, but if you have any planetary science to bring into this, please share. So I'm
Big
not
gaping
totally
hole,
sure.
my
But one of the things, I guess, one of the things that's really interesting that a lot of people don't know about Venus is that, sure, down at the surface of Venus, it is this horribly hot hellscape. But in fact, if you go up into the atmosphere, there's a certain point in the atmosphere where the temperature and the pressure are actually Earth-like. So you could stand out on the deck of your Zeppelin Venus habitat in purely an acid-proof suit, and you would be, comfortable in that, you wouldn't need to be pressurized and you wouldn't need to be warmed up. It would just be, raining sulfuric acid at you. But apart from that, it would be fine. So that's something that people, I guess, don't realize. And so I guess the question is, why is the atmosphere strangely cold when it shouldn't be, to all previous estimates?
And I don't know off the top of my head what sort of the layers of the atmosphere in terms of temperature are, but I wonder what's happening at that 78-mile position where all of a sudden it just gets frighteningly cold. And this is where, carbon dioxide can freeze at this temperature. So there's possibly snow in this very limited region, in this thin layer, only in the terminator, which is kind of neat. And I wonder too how much, because Venus's day is as long as its year, which is another thing I don't think people necessarily think about too often, but it's really neat. That the terminator probably has a really nice long time to create this really weird environment and let all these things interact and kind of, build this really weird cold spot. So
Yeah,
Venus is a cold spot.
Right. You're looking at it's about 70 to 160 kilometers above the surface, sort of in between that range, right? And you get the temperature getting down to, 80 Kelvin-ish? So cold.
Yeah, really cold.
Yeah. It's freezing carbon dioxide, which would be very strange, but I guess if the carbon dioxide tried to go any higher or lower in the atmosphere, it would quickly sublimate again.
Yeah. So I'm kind of waiting to see what else. This is from the Venus Express orbiter. I'm just kind of waiting to see what else the ESA comes out with about this, because this is really neat. I've always been kind of fascinated with Venus because it's so odd. It's just making it really odder.
One of my, I think I've mentioned this in past weeks, it all blurs together. One of my favorite missions that's been proposed for going to Venus is someone proposed building a Stirling engine, which is a certain kind of engine, and then running it backwards on the surface of Venus. So you would land the spacecraft down on the surface of Venus, and then you would take about a month or so for the spacecraft, for the rover to cook inside out. And so it would slowly be trying to dissipate the heat using the Stirling engine and use it to power itself to move around the surface. It was a really cool idea, and as usual, went nowhere. So
I haven't heard that one. I've heard of the idea of sailing like gliders through the atmosphere, where you can sort of support on the weight of the atmosphere without having to worry about landing or falling, and that just kind of bounce around and Check it out.
Well, I wonder if you could maybe you could use this atmosphere. You know, you could run some balloon up a 30-kilometer tether, and then you could run coolant down from the cold temperature down to your rover, and then warm it up. And then it could just keep, cool it back down, so you can just keep running your rover forever. So this is a possible opportunity for space exploration. That's what I think.
Right. Engineers out there, make it happen.
Make it happen, yeah. All right, well, let's move on. So Nancy, now a second story, and you actually just published this just a couple of days ago, is, and this is important, the most precise measurement of the universe's expansion. So how exactly fast is the universe expanding? Oh, you're muted, Nancy.
Thanks. It is expanding 74.3 plus or minus 2.1 kilometers per second per megaparsec. And
Nicole, can you translate that for us, please?
Yes, please.
It's not necessarily a speed, but that's the new value of the Hubble constant, which is we've known to be around the 75 regime for a while now, but actually getting a better and better measurement of the Hubble constant will tell us the universe is aged with precision, and will tell us some things about what the universe is made of. So it'll tell us some things about what the nature of dark energy is, for example.
And so Nancy, how was this research done?
Well, it was done with the Spitzer Space Telescope, and basically they looked at Cepheid variable stars. And with Spitzer, of course, they can look in the infrared, and they looked in the very long infrared. They observed 10 different Cepheids in our own Milky Way galaxy and about 80 in the Large Magellanic Cloud. And so without the in infrared, you can see through the dust and gas that's in the universe. And so without the dust blocking their view, they were able to really get really precise measurements of the Cepheids' apparent brightness, and which in turn they were able to very precisely get their distances. And Cepheids are really have been a long time. Astronomers have used Cepheids for a long time to try to get these calculations, because these stars pulse at a very steady rate, and you can kind of use that rate to determine their brightness. And so anyway, with Spitzer being able to see the stars, these Cepheid variables more clearly, they were able to make a more definite definition.
And so, this is kind of like a cosmic yardstick. This is a way of saying, the Hubble, this is a new measurement for the Hubble constant. Is this something that a lot of astronomers will then be able to sort of bring back into their calculations? I mean, if Nicole, as an astronomer, if someone says, oh, we got a new number for the Hubble constant, it's now 74.3, how would you use that?
It would go back into understanding what some of the physical constants are with better precision. Like I mentioned, dark energy, because that was one I worked on as a first-year grad student. So we know well enough to get that 13.6 billion year age for the universe, but to get something such as the physical parameters of the equation of state of dark energy, for example, because we don't know what it is, it could be Einstein's cosmological constant, it could be some kind of vacuum energy. We're not really sure until we get an idea of what not only exactly what our expansion is now, which is what this is measuring, but also the history of expansion through cosmic time.
So, I mean, would you just go back and just plug this new number into your calculations for some of the projects you've worked on in the past, and then?
Yeah, this isn't enough of a change that you would do this for most distance measurements for things that we're looking at, but it would make a bigger impact on the large scale of cosmology.
And is it possible that it might overturn some previous predictions or thinking? I mean, I know one of the big ones is dark energy increasing over time, right? I mean, this is this concept of the big rip, where you get the situation where in the past maybe dark energy was less powerful and was exhibiting less force in every square
we know it was
space, and then over time the amount that it's providing is increasing and increasing, and eventually it might start to pull galaxies apart. It might eventually start to pull solar systems apart and eventually pull atoms apart. And this is still a bit of a controversy. They don't know whether we're going to get this situation where the amount of dark energy is increasing, or it's been, it's static, and you just get this increase of the expansion of the universe, but not necessarily an actual increase of what's expanding, if that makes any sense.
Yeah. And dark energy has had an increasing. So for a while, things were dominated by light, by radiation, and things were dominated by matter. And now we're in the era where we're starting to transition to the era where things are being dominated by dark energy. And I don't know what the latest word is on whether or not there's going to be a big rip, but...
Right, I know that's still, and this is what these kinds of surveys are trying to do, is get to the heart of, is the universe going to tear itself apart at a molecular level, or will it just continue to expand forever to a sort of cold heat death?
Right, and yeah, like Nancy mentions in the article, this is the first era where we can talk about cosmology and precision in the same sentence, which is just mind-blowing, because things, error bars in the time of Hubble or Henrietta Leavitt were so huge that, there were so many different cosmological scenarios, and now we can put these tiny error bars on such important parameters.
It's like when they say...
That is really interesting.
It's like when they say, the universe has been around for 13.7 billion, 13.7, actually it's more precise, right? I forget what the exact number is, but, you can say it with that level of precision, that it's insane. So, science. Okay, so last story we're going to cover today is the 55th anniversary of Sputnik. So go Sputnik.
Yeah, go Sputnik. I love Sputnik. It's kind of crazy to think that it's only been 55 years since we started actually exploring space with probes on rockets, and we've done a lot of things. I kind of just love that as a benchmark. But Sputnik is kind of, it's just a great story, and it's a really interesting sort of catalyst for everything that came afterwards. Sputnik itself is not very impressive for all intents and purposes. It was a 22-inch sphere of aluminum with, it beeped. It had a thing inside that would change the tone of the beep depending on temperature, and batteries to run the beep, and that was it. And it wasn't, it didn't do anything. It wasn't used to triangulate this, position of major U.S. cities. It wasn't broadcasting any information. It wasn't dropping bombs. And the American scientists knew it wasn't very interesting, and they knew that it was so big and heavy because the Soviets had really unsophisticated instruments compared to the U.S. But the American people didn't see that. They saw that this thing was way bigger. It was 184 pounds, and the U.S. was looking to launch the Vanguard satellite, which weighed 3.5 pounds. And it was just this mentality of, oh, bigger is better. Which, of course, when you get down to the rocket that's launching the bigger satellite, bigger is kind of better. And there's Sputnik. There's some great recordings. I should have found a recording of the beep. But people started freaking out about the Soviet rocket power that they had that the Americans didn't have. And there were sort of a lot of things happened between August and November of 1957 to create this just intense paranoia in the States. Like in August, there had been a successful test of a Soviet intercontinental ballistic missile launched on an R-7 rocket, which was the same rocket that launched Sputnik. And that was kind of worrying, but you couldn't see that test launch in the sky every night. So Sputnik kind of made it more real. And then in November, the Soviets followed it with Sputnik 2, which was 1,120 pounds, which is huge, and it had a dog and a life support system in it. And then it became like a real, okay, we still haven't put anything up there. And then the Gaither report comes out saying that the Soviet Union might have a significant intercontinental ballistic missile capacity that the Americans don't have. So this little ball sort of ended up not personifying some person, but whatever the orb equivalent of personifying is, all this sort of growing paranoia about this non-existent missile. There's Laika, the dog. She died going up because there was not enough heat protection. But it's really interesting that this little ball just sort of pulled together all of the fear that everyone had from the growing Cold War mentality, and it just launched the entire era of space exploration. It's kind of great. It's only been 55 years since we've been putting stuff on rockets. Well, successfully. We put stuff on rockets like in the 30s, and they all blew up or died. Monkeys were smashing into the desert floor. It was bad. Yeah.
Has someone written a book about the horrible things done to animals during the space age?
You know what? Not off the top of my head that I know of. I've written about some of them.
I just got you a book deal, Amy.
Yeah, I've read some articles about the horrible things. There was a lot of the Aerobie sounding rockets. They're just launching up to about 30 miles to see how they would fare, but the parachutes failed a lot, and the landings were really hard, and there were just some really poor pigs and monkeys. But, yeah, Sputnik was the first success. That
would be, except for the dog dying, but...
Yeah, but the Sputnik 2 did get into orbit and stayed up for 200 days. That was pretty impressive.
So
before...
So, I mean, were the Russians really, or the Soviets really far ahead? I mean, the Americans, I know, if you read about this, they were, they had their, the Explorer 1, you were saying that? They had their spacecraft, their satellite they were going to be launching, and then the Russians beat them to it, right? I mean,
well, it gets kind of interesting in the sort of internal U.S. politics, because the Germans came to the Army, and they were building rockets for the Army. They had the Atlas and the Jupiter and the Juno. But Eisenhower wasn't too thrilled about sending the first U.S. satellite on a German-built missile. So he gave the first launch opportunity to the Navy, which was launching the All-American Vanguard. And this was this little 3.5-pound satellite that wasn't really going to do loads, but the missile just didn't have, I mean, quite frankly, it just didn't have the German backing and the knowledge and the know-how. The Soviets had the same. They had their own Germans, and they had their own big rocket. And a lot of it, too, was the Soviets, they wanted to put something more sophisticated up, but they were really trying to get it up first, so they cut corners, and they just said, okay, we're just going to compromise, we're going to put this really simple thing up, and we're just going to do it first. And they did it right at the end of an International Geophysical Year conference in Washington, which is lovely timing. So they're all at this big party celebrating the end of international scientific research, and like, by the way, we have a satellite. Yeah, that was good. But yeah, then of course the Navy Vanguard rocket failed and exploded on live television in December, and then Eisenhower said, "Okay, Army, your German rockets can have a shot." And they had a very limited launch window, and of course they did it. But yeah, so that was an interesting sort of. Had they given von Braun the right to launch and just said, "Okay, Army, go," they would have probably gotten up first.
I mean, a V2 rocket was pretty close to being able to go. I mean, it went suborbital, right?
Yeah, it was. I mean, these things they were doing some tests. I don't know off the top of my head how high, but there are some pictures from cameras on V2s that were launched in New Mexico that you can see. I mean, it looks like an orbital picture. It looks like a really low orbit. They were getting up there, and they could have just built on that technology and got it a little bit higher to really just get everything started, but they just didn't have the support. They didn't have the go-ahead.
Yeah, the politics of it are just really fascinating. Well, thanks, Sputnik.
Thanks, Sputnik.
Cool. All right. Well, I don't see a lot of questions today. We're going to do a fairly quick show. Like I said, there's a lot of sort of big announcements that are coming up that I know the journalists need to rock to. So I think we'll just wrap it up. But before we do, where can people find more about everybody involved? Amy, where can we find out more, Amy?
AmyShiraTeitel.com, or you can Google Vintage Space and my blog comes up, and Google Plus is probably the best place to find me because I'm pretty active over there.
Perfect. Which is here, all around us right now.
In the internet.
In the internet. Nancy Atkinson, where can we find out more of your writing?
Universe Today.
I love that place.
Yeah, isn't that a good place?
It's a great site. Yeah, highly recommended. Yeah, no, you've been. It's funny. You've been really busy today. Actually, got a ton of stories today.
Yeah, and then there's more stuff coming out, as you said, this afternoon.
I know,
so
it's going to be a crazy day. So I shall let you get back to work. Nicole Gugliucci, where can we find out more?
Hi, I work at CosmoQuest at cosmoquest.org, and you can also find me at noisyastronomer.com and links to all the crazy things I do on the internet.
And what of the many projects that CosmoQuest does, what would be the one that you think people should get involved in today?
Vesta Mappers, of course.
Vesta Mappers.
Asteroid Mappers Vesta Edition. We've got high-resolution images from Dawn, the Dawn mission. And so the scientists, even though Dawn has left Vesta, the science has just gotten started. So
Yeah, and so if anybody has ever wanted to map an asteroid, be involved in science, get your name in a journal, now is your chance.
Yes.
You can go to CosmoQuest, you can see these really cool pictures of asteroid Vesta, you can map out the craters, and your information will go back to the scientists, and they'll use it for their studies. So,
Yep.
and then you can see all the other cool scientific projects we're working on too. So, cool. Awesome. All right, well, it's great to see all of you guys this week. Thank you very much for joining me. I know you're all busy, so we'll let you all get back at it, and we will see everyone next week. I guess the next thing is we're going to do the virtual star party on Sunday night. So the stupid moon should be gone, so we'll have a better night.
Don't hate on the moon.
Be gone, moon.
Why?
All right. We'll see you guys later.
Bye.
Bye.